Hi everyone. I'm going to talk about tools that allow you to better understand what's going on in your application. And specifically, I'm going to use Babel to build these tools. So let's start by defining what dynamic analysis is. So the data you get by doing dynamic analysis means you actually have to run and execute your code to gather that data. So that's in opposition to static analysis, where you can just look at the code as text without having to execute it. So I have this little snippet, and with a static analysis tool, I'm able to... Oh, sorry. That's not bad. Oh, yeah. That's better. Cool. So if I have a static analysis tool, I can look at this bit of code, and the static analysis tool can see that I'm assigning inside the condition of an if statement, which is probably not what I want to do. So it can point at that out, there's a potential error, and then I can fix it. And replace it by like a triple equals. But just because I did that doesn't mean that my code is always going to run. And static analysis doesn't give me all my information about this code. So it might still be that this thing called R isn't actually an array, or it doesn't have a length property, or other things might go wrong. And dynamic analysis tools actually tell me like what's happening during execution. I can tell if this if statement is actually ever executed. And fundamentally, dynamic analysis is a very broad term. Fundamentally, you do it every time you do a console log statement, because you're gathering runtime data and looking at it and trying to analyze it. And these logging instructions are called instrumentation. So you capture data and then evaluate it later on. But really, you don't talk about dynamic analysis tools in that way all the time. You don't consider console log a dynamic analysis tool. So the key point generally is that this instrumentation is added automatically. And we need a way to go from the code without instrumentation to the code with instrumentation. And that's what we need a compiler for, which is what Babel is. So next, I'm just going to give a brief introduction to Babel. So originally it was called 6-to-5 because the main purpose of it was to just compile ES6 code to ES5 code that runs in all the browsers. So for example, if you have an arrow function, that's not going to run in an old Internet Explorer browser. And you need to run Babel, compile it down to ES5 code that's supported to be able to use these newer features. But then Babel changed its name to Babel from 6-to-5. And now it supports not just ES6 or ES2015, but also ES7, ES2016. Or if you're using React, you can build your JSX code with it. Or really, you can build any type of functionality, any type of code compilation or transformation that you want to do, you can do using Babel. And this is achieved using what's called plugins. So these plugins encapsulate the transformation facilities that you have. So the downside from when switching from something like 6-to-5 to Babel is that now suddenly, by default, Babel does nothing at all. So you actually have to tell it and create this Babel RC file and tell it all the things you want it to do. So you have to list all the plugins you want, for example, to be able to compile ES2015 code or ES6 code. But that's not very convenient. So there's this tool, there's this feature in Babel called presets. And that basically allows you to bundle a bunch of plugins into one thing, and you can just say, well, I want to be able to use ES2015, and I don't care about the specific plugins that I'm using. So Babel basically takes 3 steps when you run it. It compiles your code, it passes your code into a syntax tree, an abstract syntax tree or AST. That's kind of a more logical structure of your program code. It takes that, traverses that tree, and makes transformation to it. It changes that tree, and then it takes that tree that you just generated and uses it to generate program code again. And the place where Babel where plugins come in is in this kind of middle bit where the transformations happen, because Babel plugins handle the transformation parts. So let's look at a very simple example. We define a variable greeting and set it to hi, and our plugin should change that text hi to hello. So it's very simple. So we pass it visit Babel. So Babel is going to give us the existing kind of nodes in the syntax tree. And you can see a variable declaration kind of consists of this ID, which is the name of the variable, and then the init, which is the initial value of that variable. For our plugin, we need to know two things, really. One is that the type of the node that we're trying to transform is a string literal, and the other thing is that we have this value, which is the thing we are trying to change. And this is the code we need to do that. So at the top, it's just like a bit of boilerplate code to be able to, so Babel can import our plugin. But then we have this concept called visitors. And visitors are important in Babel because they allow you to tell Babel, while it's traversing your tree, what kind of AST nodes are you interested in. And in this case, I'm interested in the string literal. And then there's this path, which just gives me some information about where in the traversal process we are at the moment. And I can simply override the value of that node to change the kind of string represented by the string literal. So this is the updated AST. My string is now hi rather than hello. And then all that Babel does is kind of generate the source code again from that syntax tree. But Babel can also do something a bit more complex. So rather than just replacing, modifying the string literal, we can actually replace it with a function call. And to do that, we do the same thing as before. We still need a visitor on the string literal because we want to change and replace a string literal. But this time, we actually have to create a new node. And we can do that using Babel types. So the type of the node we want to create is call expression, and it takes two parameters. The first one is the thing that we're trying to call, and the second is the list of arguments. In this case, we don't have any arguments, so it's just an empty list. The thing that we want to call can be anything that kind of evaluates to a function. It could be a function expression, it could be a call expression that it returns a function, or in this case, it's just the name of a function that we want to call. And then once we've created that new node, we need to tell Babel that we want to update the DOM, update the AST with that node. And we get the kind of result that we have at the top of the slide. So let's look at an example of what we can do by capturing this kind of runtime data using Babel. I'm going to show a simple demo app that has nothing to do with dynamic analysis by itself. But there is a bug in this app, and then we're going to build a dynamic analysis tool to identify the bug and fix it. The tool that we're going to try to fix is this. It's very simple. It just lists how many recent contributors there were, how many recent contributions have been made to Babel by different people, and tells you how many contributions they've made, how many commits they've made. And then when you click on these people, you can see the recent commit messages that they made. So on the left, it's like the list of people. On the right, you've got commits. But the problem is that when I actually try to run this, I'm getting an error during execution. I'm getting an exception because like something isn't defined. And I want to figure out why that's happening. So the way my application should work is that I have this object, I have a name that I want to get the commits of, and then for each name I have a list of commits. And the commit then has an object, it's basically an object, and it contains things like the commit message and the time of the commit and the name of the contributor and other details. This is what I want to happen. But actually, if I look at this, rather than getting the list of commits for a particular user or for a particular contributor, I am getting just the number of commits that they've made. So that tells me that at some point, my commits by author value has changed in a way I didn't expect. So these properties have been overwritten. And the goal for my dynamic analysis tool is that I want to figure out where has this value been changed, where has this been mutated when I didn't want that to happen. And I can't just go into Chrome DevTools and set a breakpoint on that variable change, for example. So that's why I'm going to build this dynamic analysis tool that tells me where the value has changed. This is the end goal that I'm aiming towards. So in addition to every property, there's also a history property for each property in the object. And that tells me every time that value was assigned. And for every assignment, I have the value that was assigned, and also I'm capturing a call stack as a string that tells me where that change has happened. And to build this, for every assignment, I actually have to also have a separate code that runs to do the tracking, to create this new history entry for this particular object. I could do it by just like calling track assignment after the assignment itself, but to build it and implement it, it's actually simpler if we just do assign property and do the assignment in there and do the tracking of the history in there as well. So before we get started with writing the Babel plugin, we need to understand the AST for the problem that we're working with. The important thing here is we're trying to replace an assignment expression with the call expression. And we saw call expressions early on already. The call expression consists of a left part, which is the thing we are assigning to, and a right part, which is the value that we are assigning. On the left part, the thing that we're assigning to, in this case, is a member expression, which is just identifies a particular property on an object. And it's very simple. It has an identifier for the object and an identifier for the property. So let's try this out. Okay, so is that readable? Okay, so this is this tool called AST Explorer, which just allows you to kind of see the DOM, especially specifically generated by kind of Babel in this case. And if I click this transformation button, I can actually write my own Babel plugin, just like inline on this page, and try things out. So what I'm trying to do in this case is I have this existing assignment, and I want it to look like this commented out code below it. And I've got already my Babel type set up like as a variable, and I have an assignment expression visitor that I'm going to use to replace the assignment with the call expression. So first of all, I have to create my call expression. Using Babel types. And we're not going to worry too much about like the parameters for now, but the important thing is that we need this identifier that identifies the name of the property of the function we're calling. So the function is assigned property. But you can see it doesn't actually change the DOM yet, the AST yet. We still get the same output. So this is the original code, and this is the output from the generation part of Babel. So we need to call pass.replace node, or replace with, and then you can see we've now replaced the assignment with the call expression. So let's clarify a bit like what the different parts of this node are that we're currently traversing. We've got the assignment expression, which is just pass.node. On the left, sorry, the left part is the member expression. And the right part is just a value that we are assigning to. So, okay, yep. And once we have those things, it's actually pretty easy to fill out this arguments array with the argument that we want. So the first thing is the object of the member expression. Then we have the property. Then we have the property of the member expression. And then finally, the value that we're assigning. oh, this isn't value, so this is undefined. It's actually the right part of the assignment expression. So we've got something like that, and it's very close to what we actually want as the resulting kind of replacement. But the only difference you can see right now is that here we have a string, and here we just have the identifier. And if we just use the identifier, because it's part of the object expression, of the member expression, it won't be globally defined, so we won't be able to access this, and this is just an undeclared variable. So we need to make this a string. But actually things are a bit more complicated, because there's something called a computed member expression. So you can't just do a member expression using two identifiers, but also by computing this expression, and then that expression is used as a name for this particular property. So there are some situations where I actually do not want to wrap this property in a string. But the member expression already tells me whether it's computed or not, so I can add an if statement in here. So let's move the property out first into a separate variable up here. And if it is not a computed property, then if the member expression is not computed, then I want the property to not be just a property itself, but just convert it to a string. So we want a string neutral. And again, we can create that using Babel types. Okay, so that's the name of the identifier we're working with. And now you can see we've got, like, in both cases, we are handling the case correctly, and we're getting the result that we want. So we're almost done with our Babel plugin now. There's actually only one thing that's left, which is that we're currently handling every assignment expression. So if we assign something that's not a property assignment, just like something equals 44, you can see we're getting this error, and that's because we are treating the thing on the left like a member expression, even though it's not one. So before we run the rest of our code, we want to check that the assignment expression, the thing on the left, is actually of type member expression. Okay, so this is done now. We can take this code and put it into a new kind of file in my application that I showed you earlier. We just saved it in like Babel plugin.js. The next step, we have to add it to the Babel RC file, or wherever you define what plugins you're using. And instead of using a name of the package, for example, like ES2015, which is the name of this preset, we can just use a file name in here. Cool, so hopefully, okay, so if we reload this page, this time we're getting a different error because we haven't actually defined the assign property function yet. So let's fix that. To begin with, we're going to define a global assign property function, and just call through to the actual function, the property assignment we want to make. So we have the object, we've got the property name, and the value. And then simply we can convert that to an assignment like this with the computed property. And now our application is kind of working again, but we still have that bug that we had before. And if I click on this and look at my commits by author, nothing has changed yet. But because we have this instrumentation, because we have this hook that allows us to track every assignment, we're now able to track that data. So first of all, we need to figure out the name of that property, of the history property. And we're just going to append history to that. If the history property does not exist already on that object, we need to assign it to just an empty array. And then finally, the thing we really care about is tracking the history and creating this history object. And this history object just has two values. The first is just the value of the assigned value, the value that has been assigned to that property just now. And the other thing is the call stack. And to capture a call stack, we can just create a new error object and get the stack property of it. And that is going to give us a string showing the current call stack. Again, I'm going to reload my application. And you can see that suddenly I'm getting all these history entries on this page. And that's because the way I'm rendering this is I'm looking at this object and I'm rendering every single property that's in it. So by adding this extra instrumentation and adding all this tracking, our object has changed in such a way to kind of break our application even more than before. So what we need to do is we need to prevent these properties, the history properties, from appearing in like a for-in loop. And to do that, we can change our object and use a slightly more kind of complicated way to assign a property using object.define property. So it takes the object that we're working with, the name of the property, and then rather than passing in just a value, we pass in what's called a property descriptor, which could have like a setter or a getter, but also can just do a value like before. But the important thing is now we can say we do not want this property to be enumerable. We do not want it to show it up in this for loop or this for-in loop. And now we fixed that problem. So if we can pause on this error and look at this object, we see the history in here. And we can see, first of all, it was assigned to this array of commits, which is what we wanted. But then there was a second assignment to just one. And we want to figure out where that assignment actually happens. And to do that, we can right-click on this and store it as a global variable. We're just going to move this into the console. And in the console, it's going to be more nicely formatted, so we can actually quite easily navigate to the different places in the code. So if I click here, all you're going to find is this assignment here, where we actually capture the call stack. But really, this particular value doesn't matter to us, so we have to go one step up. If we go this step up, we find this function called mapObject. And what this function does, it is similar to the map function you have on an array. So it takes an object and it mutates that object so that for every property, the value of the property is transformed by this function fn. Now, unlike what I have with like array map, when I do this, what's happening is that I'm actually mutating the original object, and that is why I'm getting the bug that I had before. So if I want to fix this and make my application work again, rather than mutating the original value, I'm going to create a new object and assign to that instead of the object that's passed in. So now when I click on here, it still doesn't work, unfortunately. Oh yeah, probably because it hasn't compiled yet. Okay, so now it does actually work, and it kind of shows you the comments again. So we could use this dynamic analysis tool to be able to kind of find where certain things happen in our application, because a lot of the time you're able to kind of track more history information about your program state than you would normally have in a debugger. Okay, cool. Okay, so let's have a look at a few other examples of these kind of dynamic analysis tools in JavaScript. So this is a project from a talk called Visualizing JavaScript Execution. And it gives you these spark lines for all your numeric variables in your code. So in this example, it kind of shows you the history of that value. So for the counter I, it kind of goes from 0 and up to 7. Whereas the a variable has kind of a zigzag shape because the value keeps going from negative value to positive value. And in that way, it's kind of a bit similar to what you just built. So rather than tracking the history of an object, what this is tracking is the history of a number. There's also a tool called dlint, which is similar to kind of jslint or eslint, but rather than being a static analysis tool, it uses dynamic analysis. And that means it can tell you things like, for example, whether a function is being called with more parameters than it actually has, or if you concatenate a string with undefined, that's probably not something you want to do in practice. So those kind of situations, it can point out to you and alert you to them. Or similarly, if you have a computation that ends with not a number, probably also something that you want to look into. Similarly, this is a tool called JITprof, and what this does, it's basically a performance tool, and it looks at your code and how it behaves and how you create your objects, and based on that, it can tell you if there are certain things that are hard to optimize for your JavaScript engine. So there are certain things, certain optimizations you can make, so the JavaScript engine can generate more efficient machine code. This is a tool that I've been working on. It's called From.js, and it kind of allows you to inspect an element, and it aims to kind of describe more the relationship between the JavaScript source code and the actual final DOM as a result. So, for example, if I inspect this element, it's going to show me all these details about it. Like, it's going to tell me where this HTML code was actually inserted into the DOM. But I can also see where the code, the string itself, came from originally. So in my to-do app that I had here with the kind of React to-do MVC app, if I look at that, it can tell me that the data comes from local storage. Or if I create a new to-do item, it would kind of form in the input element. So the goal here is to kind of allow you to explore your application a bit more and allow you to see also the relationship between different parts of your code and how values travel through those. So in this talk, I've been talking about instrumentation, and I've been very much focused on talking about compilation and Babel. But that's not the only way to kind of create these hooks. The other way is using method packaging, because in JavaScript, you can often override a lot of the native methods. So you can create a wrapper function around the native method, override the native method, and then capture your data there. So this is an example of how you would do that. I want to find out all the places where I'm creating a new element using document create element. So first I need to reference to the existing create element function, because I still want to be able to create elements. And then in the overwritten function, what I do is I create the object, I capture a call stack, and then return the element. And the goal of kind of doing it this way is that it allows me to write this Babel plugin, but it's not going to affect, not Babel plugin, it's going to write me to overwrite this function without actually interfering with the normal execution of the source code. The only difference is that this time, if I inspect an element that was created in this way, for example in the DOM inspector, I'm actually able to find out the location where it was created. This kind of dynamic analysis has a few limitations. So the first one is execution speed. The fact that you have instrumentation means you're running more code, and especially operations like we saw earlier with capturing a call stack as a string, that's quite expensive because JavaScript engines really aren't optimized for doing that 10,000 times. Another issue of memory, not just does the kind of track data have to be tracked, but also what we saw earlier with the object history. If we store the history of all the values, that means the garbage collector can no longer do its job because every value that has ever been assigned to an object is still somewhere in the history and cannot be removed from memory because JavaScript doesn't know that the value is not needed anymore. And finally, a lot of these tools break existing functionality. So we saw that first with the kind of issue where our history property was enumerable, and we fixed that. But actually, if you were to use object.keys, we would still be able to get all the history properties in that result. But again, like you couldn't override object.keys to kind of deal with that problem. But if you modify native objects or do those kind of more invasive things rather than just like doing a console log, it just means you have to do more work later on to kind of fake a reality to the browser that everything is still as it should be. The last thing I'm going to talk about is this thing called chakra core, and it kind of steps away, no chakra core, so it steps away from capturing data in JavaScript and actually does it as part of the JavaScript engine. So chakra core is a JavaScript engine like V8, and Node Chakra Core is a project by Microsoft that allows you to run a Node program with all the Node APIs with Chakra Core instead of V8. And what this allows you to do, it allows you to do these kind of time travel debugging features where the entire program state is captured, and rather than just stepping forwards in your debugger and kind of seeing how values change and how things are calculated, you are actually able to step backwards, and all the state is kind of completely reverted. And the way it does that is by just capturing snapshot all the time and capturing other data that allows it to completely reconstruct all this information. So before doing the debugging, you have to kind of enable all this kind of logging functionality first. So if you want to learn more, here are a few resources. A lot of them are kind of different tools, but also like other presentations that kind of give a kind of different perspective on dynamic analysis. So slides are online as well. Thank you for your attention.
Okay, guys, so we have a couple of minutes for questions. Do you have any questions? No questions, really? Are you kidding? Come on. We have no questions. All right then, thank you.